Okay, chemistry time. Today we are talking about light and quantized energy and the electron. We could, if we were being really, I don't know, pedantic, we might try to call this quantum mechanics, and indeed we will talk a little bit about quantum mechanics. And the reason I kind of like to do that sometimes is because since when the first time you hear about the idea of quantum mechanics or quantum physics, you think, well, that sounds cool. I'm going to be a quantum physicist, and that is what we're doing. That's not wrong. It's just a little bit, as I say, pedantic. So we like to usually call this light, quantized energy, and electrons. Your bell work asked you to explain the relationship between mass and energy. If you remember from last time, we talked about mass and energy. Maybe the most basic relationship they have is that those two things make up what? Mass and energy together make up, I would not go that far, Fate. A true empiricist, someone who only thinks that the world is observable, would say what you said is true. But the observable universe, right? Everything that we as human beings in our physical nature can observe is either matter or energy. Or there's a third, we don't talk about a lot, especially in the West, because this is not the way our brains usually work. We're usually focused on the concrete and the apparent and the positive, but there is a negative, which is space, right? The universe is made of space, matter, and energy. And a lot of times we just think space is what fills in the cracks, right? Space doesn't really matter. It's nothing. How could it matter? But it is a part of the universe, right? If there was no space, all of the matter and the energy would just be there. I mean, there'd be nothing in between. There'd be no differences between them. And so matter, energy, and space are related in that they make up the whole universe. But what else? How else are matter and energy related? Let me try to draw this out of you about your lab. In your lab, you observed both matter and energy. Tell me about the matter in your lab. Yeah, you use various compounds, right? You had, well, I have blue out, so I'm going to draw the Bunsen burner in blue. You had bluey, right? Bunsen burner, the blue flame, and you had an evaporating dish, and you put in boric acid, and it green fire. Remember that? You remember that part? Or you put in lithium chloride. Some people call it crimson. I call it pink fire, right? You put in strontium. So what's going on there? You put in matter of various kinds, and energy of various kinds comes out. So do you see that there must be a relationship between energy and matter, because the type of matter influenced the type of energy that got out, right? Does that kind of make sense? Yep. Let's dig a little bit deeper into what's going on here as a way of talking about the relationship between matter and energy. One thing is that what is different about these kinds of energy emitted? The color. The color is different. Do you remember, I think from 8th grade science, what physical property of a light wave is different that causes different colors? I think I see what you're getting at, but that's not the answer I'm looking for. No, not energy. What part of remember, we diagrammed light waves sometimes. Frequency. Yeah, frequency is what I'm looking for. So we have here a light wave, and we have a frequency demarcated by the Greek letter nu. This is the Greek letter nu, which is frequency. Measured in what unit? Do you remember? Hertz. Good. Thank you. I hope you're also writing this down. I mean, it's obvious to me that you knew it, but you should also probably write it down. So the frequency, how many waves pass in a given amount of time? If it's measured in hertz, it's the amount of waves that pass in a second, is the color of the light. What the light wave in its physical nature manifests as frequency, our eyes and brains perceive as color. So different frequencies of light are being emitted by these different compounds. Do you see that? You did see it, right? That's what it was. You, as a high school observer of this, saw different colors, but that is the same thing as seeing different frequencies. You saw different frequencies of light when you put those different compounds in. So there must be some relationship between the nature of matter, because we had different kinds of matter, and the kind of light that is emitted. Again, so we have the frequency. As a little, I guess, side note, what else is true of this wave? What's this that I've just demarcated there? Wavelength. Lambda, the Greek letter lambda, the lowercase Greek letter lambda, is wavelength. And what in the SI do we use to measure wavelength, usually?
Nanometers.
Sure, nanometers. I'm just going to put meters because we do use the various prefixes of meters, especially nanometers, but it's the base unit that we use for length, wavelength, because it is a length, is meters. If I then put this dotted line of the baseline, or the origin, what is this height? From the origin to the height of the, oh wait, what's this little guy? Crest? What's that? What's this distance from the origin to the top of the crest? Remember? Yep, you got it. Good job. Amplitude. Also measured in meters. It would be a low number of meters for a light wave, but it would be. And then just for light, if we factor the wavelength and the frequency, we get the speed of light, which we indicate with the letter C, where C is the speed of light, a constant in a vacuum. Speed of light. And it's not only measured in meters per second, it is, but it's 3.0 times 10 to the 8th meters per second. So it has a value. It has it's a constant. In fact, it's one of the most foundational building blocks of our universe is this speed limit of light in a vacuum. As we currently understand in physics, nothing can go faster than this. This is the max speed of, and things start to break down at that level, but this is the max speed of the universe. Time has no meaning when something moves at the speed of light. All the other things that we normally think of in our daily life as constant, length of objects, the measurement of time, mass of objects, momentum of objects, that all completely breaks down when it goes really at any speed, but especially as it approaches the speed of light. So C is the speed of light, measured in meters per second. It's 3 times 10 to the 8th meters per second. What's up?
What about the speed of sound?
The speed of sound is not so much a limit. It's a, we're not talking about sound right now, but I'll answer your question and then we'll move on. The 3.0 times 10 to the 8th, yep. The speed of sound is governed by how fast the particles can vibrate in a medium. And that's not so much a physical, it is a physical limitation, but it's not a universal physical limitation like the speed of light is. We said already, lambda is the wavelength, measured in meters, and nu is the frequency, measured in hertz, which is equal to inverse seconds to the negative first power. And so you can see if we multiply meters times 1 over seconds, we end up with meters per second. That's how we measure light. And I already said, but what is true of C? It's a constant. That's why we use the letter C for it. It's a constant. And so if this number can't change, what must happen? In my various frequencies of light, which my human eye and brain perceive as various colors of light, if the red has a lower frequency, what must be true about its wavelength compared to the violet? It must be longer. If frequency goes down and gets smaller, wavelength must get bigger. These two must be inversely proportional because this one stays the same. You with me? So some of your calculations on your test and on your worksheet and on your chapter review will be using this calculation while remembering that C is a constant and stays the same. Pretty simple math, actually. It's even simpler than a normal, like 3-variable linear algebra problem because this one doesn't change. Now, it's a little bit complicated mechanically because the numbers we're working with are very large or very small. but it's not, like, I guess I should say, to type it in the calculator might be complicated, but it's not hard math. Do you agree? Do you have questions about how we would use this frequency formula or this wave speed formula to find frequency and wavelength? And this is for what? What kind of very basic thing are we talking about? Light. Light. And I can you see, Fate, if that's showing up on camera, this little table? I want to show the electromagnetic spectrum. Is that showing up?
Yes.
Okay. So that, you can pause it there. That is the electromagnetic spectrum. And you can, if you're present here with me in real life, would you please turn to page 139 so we can look at it together? So you can see, depending on the wavelength and frequency of light, we give the light different names. What's the kind of light that we're used to dealing with? What we might just in our normal lives just call light is what on this graph, and where is it? Visible light. The rainbow. Red, red, orange, orange, yellow, green, blue, purple, 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 purple. In a rainbow light show. Light shining colors, like the rainbow. Underwater rainbow. All the beautiful colors that Eliana chooses to write her notes in. Let me just knock them on the floor for you too, Ellie. The beautiful colors that Eliana chooses to write her notes in are like unto the rainbow, right? They're different what's of light. We would say colors. Like if I went to the pre-K class and said, oh, these markers and pins are all different, they would say colors. That's true. I'm not saying that's wrong, but they're also different. They're reflecting different and frequencies of visible light. And it's so much broader than that, right? Looking back at our electromagnetic spectrum, it's more than just this tiny little sliver that we can actively see. There is, if we go up in frequency, as frequency increases, what's the next one after visible light? Ultraviolet. What do you know about ultraviolet?
You can't see it.
You can't see it. Ultraviolet, above the violet spectrum. What else is true about ultraviolet? What else have you heard about that?
And some animals.
Birds, yep. Some animals can see in the ultraviolet part of the spectrum. Excuse me.
The sun's radiation.
The sun's radiation that damages your skin, right? The radiation that both makes it through the ozone layer and you can't see and is emitted by the sun, that causes things like sunburn and suntan and skin cancer. Okay, above that in frequency, what do you know about X-rays from?
While you see through objects.
Yeah, you can see through certain objects. The X-ray will pass through objects, and so the way like an X-ray machine works is that it passes X-rays through your body, and then there's a receiving plate behind you, and the image of your bones will be blocked, or the bones will block the X-rays, and so you'll get a shadow of where your bones is, and it passes through soft tissue, and so that's how they can see that. And then the next one up, the next highest frequency is gamma rays. What do you know about gamma rays?
They are
not good for you. That is so true. Yeah, we don't. They're very high energy. Higher frequency also means higher energy. We'll talk about that in a second. Very high energy, very ionizing. We call ultraviolet X-rays and gamma radiation ionizing light because it has enough energy that it can knock away electrons from atoms, which ionizing, like we talked about, but also has the ability to ruin things like your DNA, your cell membranes. It is toxic is not the right word, but it's biohazardous. I don't even like that. It is, what's the word I actually want to use? It destroys cells. It causes lysis. That's what it is. Cytolysis, I think. Cellular lysis. It causes cells to be damaged. In your body, either that could kill the cell, or it could damage the cell enough that the cells around it could kill it, or it could damage it in such a way that it mutates and somehow circumvents the autolysis process and causes cancer. And so all of those things are bad. And so we try to stay away from those kind of high frequency lights, right? If we're in the sun, many of us will put on sunscreen to avoid the ultraviolet radiation. In the X-ray technician, that person will stand in a whole other room, and even if you are the one receiving an X-ray, they will give you a lead apron to wear so that your reproductive organs do not get the X-ray on them, because that could ruin, if it damages a cell in your arm, fine. If it damages one of your reproductive cells, that might be the cell that gets passed on to your child, and now they have problems. And so a lot of times if you go to the X-ray, they'll give you a lead apron to wear. I'll ask you a question.
Was your meaning cellulitis?
No, not cellulitis. I think lysis is what I was looking for. It's not the exact right word, but and then going down in frequency, below the red end of the spectrum, which is the lowest that we see is red, the lowest frequency that we see is red. Below that is infrared, right? Below red. Below that, microwave. Now let's talk for a second about microwave. I just said that those ones higher in energy than visible light can be damaging to cells, but microwaves, you wouldn't want to be in a microwave, right? You wouldn't want to microwave a hamster. You might, if depending on who you are. But how is the microwave oven damaging if it doesn't have as much energy? Look, the microwave doesn't even have as much energy. It doesn't have as high a frequency as even visible light. So why is that, do you think? I'll tell you. It's because of resonant frequency. Resonance is a phenomenon that occurs when waves of a particular frequency vibrate another object with that same frequency. If I had thought we were going to talk about this, because I wasn't really planning ahead, I would have gone some tuning forks out. But if you vibrate something at a given frequency, sometimes the things around it will start to vibrate that frequency too. And water's particular resonance frequency is in the microwave range. And so microwaves are tuned to the resonance frequency of water, meaning that when the microwave oven is on, the water molecules start to vibrate really fast for the amount of energy that's put in, which of course, since most things that we deal with in our daily life, foodstuffs, hamsters, have water in them, that water vibrating really fast means it heats up a lot, and that's why it's good for our food and bad for our hamsters. And below microwaves, we have radio waves. And you're familiar with that from B94.7, the blast. Okay, also, I bring up that because B94.7, the blast, the way old-timey radios worked, and to some extent the way modern radios work, is that you would have a crystal in your radio that when you tune it, you tighten a coil of metal around the crystal. It's a quartz crystal, and depending on how tight that metal coil was, it would resonate with different frequencies. And if you tune it to 94.7 megahertz, million hertz, which is 9.47 times 10 to the 7th, yes, 10 to the 7th hertz, that's in the radio frequency. And so you can tune it to that, and that crystal will resonate, and it would amplify into the speakers, and you would be able to listen to B94.7, the blast. Not a sponsor. Other brands are available. Now, here's how this relates to quantized energy. Quantized means, quantum is kind of a fancy word that really just means increment. A quantum is an increment. So when someone talks about quantum mechanics, they're talking about the fact that on the very smallest scale, energy goes up in set amounts, like a ratchet. Like a ratchet strap or a ratchet wrench, that it can be on one little pawl or it can be on the next one, but it can't really be in between them. I know in real life that that's not true. You could be in between them. Or like on the stairs, you're either on one stair or on the next one. You can't really be between stairs. And I know in real life that's not true. I'm just trying to make an example. So quantized means that it can be here or here, but it can't really hang out in between. That's what it means for energy to be quantized. And that's how it is in the atom. In our atom, that's the nucleus, electrons can exist in these discrete, what we usually indicate as orbitals. Now, this is the Bohr model of the atom. This is the Bohr model of the atom, B-O-H-R, named after Niels Bohr, Swedish physicist, I think. Was he Swedish? Come on, buddy. Danish. I'm so sorry. I'm so sorry, Sweden. How dare I confuse you with Denmark? They are both Scandinavian. I should have just said Scandinavian physicist. But the Bohr model of the atom tells us that electrons exist in quantized energy states. Electrons exist in quantized energy states, meaning they have increments. It's either in the first orbital or the second, but not in between them. Now, how does that fit with our electron cloud model? Remember, we said that in an electron cloud model, it could be anywhere within this cloud, kind of at random. And the truth is that it's a little bit more complicated than either of these diagrams. That's the point of models. They simplify. That in reality, the electron exists as a wave and as a particle, or you could say a wave or a particle, and the frequency of that wave relates to how we would diagram it. So it's not really existing like Mercury orbiting the sun, but when it has a certain amount of energy, it behaves as this kind of wave, and then when it gets more energy, it behaves as this kind of wave. Your book does a much better diagram of that than I do. If you go to page 149, you can see there's a picture of the waves as they gain energy. It's not so much, we often diagram it as the electron leaping from one circular orbit to the next, while also knowing that that's wrong. What's really happening is that it is changing, and then again on page 154, it shows you something like the actual physical shapes. The shape of the orbital itself changes. That's what it means for electrons to exist in quantized energy states. So we still call them, though, energy level 1, 2, 3, and 4, and 5, etc., ... So electrons can exist at energy level 1, or 2, or 3, but not 1.5. There's no such thing as energy level 1.5. And that relates back to our flame test. What's happening in the flame test is that you put the lithium carbonate, I've got my lithium carbonate color here, into the fire, and it absorbs some energy from what? The fire. The fire is emitting energy. The fire is a chemical reaction that's emitting energy. And when you put the lithium chloride in there, it absorbs a little energy. And when it goes back to its ground state, so let's say the electron moves from energy level 1 to 2. It absorbs energy to get there. And then when the electron gets unexcited, when it goes back to its ground state, it emits energy. And it only emits energy of a certain frequency. It actually only absorbs energy of a certain frequency too. But since you have a whole bunch of energy of all different frequencies, you don't notice which kind it's absorbing. And then when it goes back, it only emits that frequency, and you have enough lithium chloride around, it actually visibly changes color. You give it energy from the flame, and then it emits energy of a certain color. And the way we calculate what kind of, or the amount of that energy is given in this equation. Energy equals Planck's constant, energy of a photon, or energy of a quantum, which is just the lowest amount of energy a thing can gain, is equal to, in both cases, Planck's constant, which is denoted with this kind of beautiful cursive S, times the frequency, which is nu again. So E is energy. What do we measure energy in again? Do you remember from physical science? Joules. Planck's constant is 6.626 times 10 to the negative 34th joule seconds. And nu, again, is frequency measured in hertz. Yep. These are all true for both the energy of a photon and the energy of a quantum. Let me make sure I wrote down the Planck's constant right. Yep, that is Planck's constant. Now the last thing before we go, I'm going to tell you the concepts behind this because we don't have very much time, and then we will work on how we actually do it in class. But and is it okay if I erase the diagram of light? Does anyone mind if I erase the diagram of light? Okay. Fate says yes in Russian and then no in German. The Russian word for no, Fate, is niet. So this is how we calculate the energy of a photon, or the energy of a quantum, which is the level of energy in an electron. And the way that electrons orbit, and use that word loosely, because remember, the electrons are not actually like planets around the nucleus. They're waves, and they're kind of popping in and out of existence in various locations around the nucleus, but that is commensurate with the energy that they have as per their shape of the orbital that we just talked about. We still do diagram them this way because it's easier, right? We could, and I guess sometimes do, diagram them like this on the top of page 158, where we just show the shapes of the electron orbitals, but that's crazy, and that would take tons of time, and we have to be really good at 3D drawing. And so instead what we usually do is just write out the energy level and the number of electrons in that energy level and its orbital shape for a given atom. So let's just start with hydrogen. How many electrons does hydrogen have? One. At its ground state, the one electron that hydrogen has, which by the way we know it has one because it only has one proton, has this configuration, 1s1. That's how we say that. Where 1 is the principal energy level, which is this, right? What orbital it's in. S is the shape of the orbital, as like what we talked about. If you want to go back and pause on that picture from 154 we talked about a while ago. And this little baby 1, which we don't pronounce as raised to the first power or squared or cubed or whatever, is the number of electrons. Since hydrogen has 1, it's in energy level 1. Next one is helium. Helium it's the shape of the orbital. There are 4 shapes of orbitals. S, which is a sphere, P, which is a dumbbell, D, which is, most of them are like clover shaped, but there is one crazy one, and F, which are altogether crazy. And we'll go through those when we go over your worksheet. The next one is helium, which still, its electrons are in principal energy 1, still in the S shape, and there are 2 electrons. So this is helium, the ground state configuration for helium. Lithium now has 1s2, just like helium, but then it also has 2s1. It has another one in the second energy level. Look at how many total electrons does lithium have. You can tell by the baby numbers. How many total electrons? 2 plus 1 is 3. Does it make sense for lithium to have 3 electrons? Yeah, because it has 3 protons. What about beryllium? What do you think that one's going to be?
1s2, 2s2.
1s2, 2s2. Do you see the pattern, kind of? In the second energy level, we can also have p orbitals, though. And so boron is going to be 1s2, 2s2, 2p1 is boron. There's a chart on page 100. I'm sorry, I turned the wrong way. There's a chart on page 156 called the Aufbau diagram, which is related to one of the principles of this, called the Aufbau principle, which shows us the order in which electrons fill up their energy levels. And it always fills from the lowest energy level to the highest. That's the Aufbau principle. And the electrons also have spins. So in our hydrogen one electron spins up. In our helium one, we have 1 electron spinning up and 1 spinning down. In our lithium, 1 up, 1 down, and then another 1 up. Beryllium, 1 up, 1 down, 1 up, 1 down. And in boron, 1 up, 1 down, 1 up, 1 down, 1 more up. Electrons can have either an up or a down spin. That's just the way. That's one of the very basic properties of matter. They can have a spin, and it's not quite the same thing as a physics spin, like when something is actually physically spinning, but we call it that anyway. And the Pauli exclusion principle says that only 2 electrons can be in one of these suborbital boxes, and they have to have opposite spins. We will work more with these. I know this is not the totality of information you will need to do a good job on your electron configurations, but this is the basic concepts that I hope once you have worked a little bit on your worksheet, which we will do on Monday, when you come back and watch the video, be like, oh, now that makes sense. Now that makes sense what he was talking about. Do you have questions about energy, light, and quantized electrons, or whatever I named it? Light, quantized energy, and electrons? I got the words right at least.
Yeah.
Can we go is your question. Yeah, I guess. That's fine. Bye!